Well, we've almost made it. Don't give up yet. We still have this final. The final is worth 20% of your grade, so it's a pretty significant amount. Wednesday, the final schedule is set up for 2 hours per final. So instead of meeting on Monday, we're meeting on Wednesday. We won't meet after tomorrow. We won't meet until Wednesday. On Mondays, they have set up Monday, Wednesday, Friday classes like 7:30, 9:30, 11:30, those times. And Wednesday is your even 8:30, 10:30, 12:40. So on the final, there will be 20 problems. And to try to cut down an entire semester to 20 problems, it's kind of difficult, but there will be a few of everything rather than a lot of any one thing. So we'll go through today, kind of remind you of what we did, especially way back about 3 months ago when we started this stuff. But best way to study for the final is to go over your old tests, and so we'll be looking over that today and tomorrow. Let's see. Test 1, we looked at a lot of limits. And then we got into a little more of the details of it. But Test 1, the first half of Test 1 was basically, here's a limit, find the value of this limit if it exists. Sometimes we found that it did not exist. But there's several different types of finding the limit. Sometimes we were able just to plug in the value, such as that. Well, the easiest way to calculate a limit is by just plugging in the x value. Most of the time it doesn't work, but that's the first thing you should do. Try that first. In this case, we get 6 minus 4, or 2. The limit as x approaches 2 is a value of 2 as well. Okay. Now, of course, I won't give you very many, if any, like that, but just to keep you honest, to make sure you know that is a possibility. A lot of the limits will be a fraction, and where whatever the top is, whatever the bottom is, and whatever x approaches, many times we ended up with 0 over 0 if we just plugged in the x value. And that's a case where you've got more to work on. You can find a limit if you do certain simplifying, lots of simplifying. And the easiest thing to look for, factor the top, factor the bottom. A lot of times we have the same factors, top and bottom, that we cancel out, and that's usually what our problem value turns out to be. So factoring is one of the possible ways to simplify. Another way is if we have a complex fraction, like problem number 2 on test 1. I'll just kind of pick out some, explain what we're looking at here. 1 over 5. Now, if we plug this in, plug in 3 for x, well, we'd get 1/5 minus 1/5 in the numerator. We get 3 minus 3 in the denominator. Again, the 0 over 0. So, good indication you got more work to do. Now, when we're looking at a complex fraction like this, the numerator has fractions in it. Sometimes the denominator will also have fractions in it. There are different ways to do this, but the kind of quickest way, maybe not the easiest, but that'll depend on your own personal preference. One thing we can do here is multiply the top and the bottom by the least common denominator of all the kind of secondary fractions, like x plus 2 and the 5. Well, the denominator is just all over 1, so we don't have to worry about that. So multiply top and bottom by 5 and by the x plus 2. What that turns out to give us, multiply 1 over x plus 2 times all of this, what happens? Okay, the x plus 2 would cancel in that part, leaving a 5 for the first part. Then we'll have minus and multiply the 1/5 times all of this. What's left there? The x plus 2. Now careful, this is the quantity of x plus 2. Okay, we have minus, I guess you could think 1 minus 1 times the quantity of x plus 2. And then the denominator, well, there's nothing really to simplify there. We've got our x minus 3, we've got 5, we've got x plus 2. Now, we've got a little more simplifying to do, but at least we've gotten rid of the complex fraction. So we'd have 5 minus x minus 2 over x minus 3, 5, and x plus 2. This one's a little tricky because the numerator turns out to be what? Three minus x. Well, to be able to cancel that with a factor in the denominator, we actually need what in the numerator? The x minus 3, which means 3 minus x needs to be rewritten how? And unfortunately I'm running out of room, but I think we can fit it all in there. So factor out a -1, and that'll turn the numerator into one part being the x minus 3. But that leaves us with the -1 in the top. X minus 3 divided by x minus 3. And now we're ready to plug in, finally, the x equals 3. I guess that's the only spot left for x equals 3. So we've got -1 over 5 times x plus 2, and we end up with a limit value of -1 over 25. Okay. So there's another somewhat common limit to calculate, simplifying the complex fractions. Okay. Now, another limit problem that is fairly common is you're rationalizing the numerator, something like this, number 5 out of test 1. Plug 3 in for x, and once again we end up with a 0 over 0. Now, how do we simplify this radical? How do we simplify? Mainly the top part is a good indication of what to do. we're going to need to multiply by the conjugate. We need the opposite sign. And again, we have to do that top and bottom. Technically, what we're doing is multiplying by a value of 1, but we're just changing the form of it to make it nicer and hopefully make it nicer and simplify for us. So as we multiply the numerator out, square root times itself leaves us with the x plus 6. Then the outsides and the insides, multiply them because of the opposite signs, they cancel each other out, and then we're left with the last minus 9 there, which that would be our numerator. Don't forget about all this in the denominator. But the numerator would simplify to x minus 3. In the denominator we have x minus 3 and then times the square root. Well, as before, as with almost all of our limit problems, we'll be able to cancel something, and this time we're left with 1 in the top. We can go back to our limit as x approaches 3, 1 over the square root plus 3, and this time we get a value of what? Okay, plug 3 in, square root of 9 plus 3, 3 plus 3, we get 1 over 6 for that limit value. So lots of little details there, but those are the 3 main forms of the limits. Simplifying is the key. Lots and lots of simplifying. Lots and lots of algebra, as you've probably gathered through the entire semester. It's not really the calculus that's hard, it's the algebra that continues to crop up that we expect you to know. And that sometimes is a little difficult. But there's your limits. Calculate limits. You can bet you'll have at least one of those, if not maybe even 2 or 3. But be finding limits. Test 1 was pretty much all finding limits, and then the last few problems were using the limits to find different things. But the next couple of problems on test 1, 10 and 11, are using a graph to calculate a limit. And I'll take a look at some examples there. Number 10 on test 1, well, I'm not going to be real accurate with it, but kind of we'll hit some of the details of it, and that's pretty close. Units, well, I didn't draw it to scale by no means, but let's say I'll just kind of draw a piece here and get our x values. A couple of the main x values. There's our horizontal axis anyway. The vertical axis is way off. I drew it pretty bad, but we can at least talk through this. What can we say about... Oh, I guess I drew it wrong. This should be a solid dot here. What can we say about the limit as x approaches -2? Okay. This one does not exist. D and E is fine for does not exist because the limit from one side, from the left side, approaches this particular y value. The limit from the right side goes off to infinity. What must happen for a limit to exist? Okay, they must approach the same value from left and right. So what about at -8? Okay, the limit as x approaches -8 will be this value. The limit exists, goodness, there we go. And that, well, to show how bad my graph is, on the test that's actually would be way down at a y value of -6. So I kind of scrunched it up a little bit. But that limit's -6. But why do we have the point here? What's that tell us? That's the y value for the function, f of -8. And again, looking at the graph, this is actually should be at -3 for the y value. So those points, well, the limit exists at -8. The function value exists, but they're not the same value, which leads us into, what do we call that? Discontinuity. It is not continuous at -8 because the limit, even though the limit exists and the function is defined, they're not equal to each other. But we can pick a lot of other points, even uninteresting points like x equals 0. Well, at x equals 0, the function is continuous because the limit exists and the function value exists, and they happen to be the same value as well. So a little bit of some of the other problems later on. We'll talk about continuity and discontinuity, what types of discontinuity we have. But anyway, the limit at least does exist at -8. What about at 6? What can we say about the limit at 6?
There's no limit from the left, but there's a limit from the right.
Okay. From the right, x approaches 6 from the right, we will get a value, and on our graph, this is y value of 5. The limit as x approaches 6 from the right would equal 5, which, because of the solid dot, that's also actually the function value when x equals 6. So that solid dot tells us actually a couple things, function value and the limit from the right. But what about the left? From the left, well, it is approaching a value. It's an open circle, but that's okay with limits. This limit, as x approaches 6 from the left, again, looking at the graph, it's at the y value of 2. Okay. But because one side is 5 and the other side is 2, when we say x approaches 6, we would have to say the limit does not exist. But with the plus or the minus up here in, looks like the exponent, that means one side or the other side. Both of those one-sided limits exist. They just don't equal the same number, so the overall limit does not exist. Okay? Questions on that? Or other questions that this graph may introduce here? Now, this was based on problem 10 off of test 1. Problem 11 is just like this, except it introduces a couple parts with continuous and discontinuous. And then 12 through 14, instead of being given a graph, we're given a function, some possibly piecewise. Is it continuous or is it discontinuous? If it's discontinuous at a certain x value, is it removable or is it non-removable? And we can kind of illustrate that from this graph as well. At -8, we said that we would have a discontinuity. Is that a removable or non-removable discontinuity? This will actually be a removable discontinuity. Because we can replace that one point and make it continuous at that point. If we move this dot here down to where the hole in the graph is, then we've actually plugged that hole, making it continuous. So that's what removable means. If we can replace that hole with one single point, then it turns into continuous. Where would we find other discontinuities? Okay, at -2, we talked about that already. With the limit does not exist, so immediately we can say we have discontinuity there. So one of the conditions of continuity is the limit has to exist. Okay, and where else? Okay, at 6 as well, the limit as x approaches 6 does not exist. And both of these have the same type of discontinuity. This would be the non-removable discontinuity. There's not just a hole in the graph there, it's a jump. Okay. Now, in problems 12 through 14, we're given functions, and to be able to tell discontinuity there, well, let's take a look at number 12. Where will the discontinuities occur? What would we be looking for there? 0 for what? For the denominator. Okay. So let's go ahead and factor the denominator. Let's see. +5 and -4. So we have discontinuity at x equals -5 and x equals 4. Now, are these removable or non-removable? Well, that depends on actually how the numerator factors. What's it factor into? Okay, +5 and -2. And, well, that shows us x plus 5's cancel out. If we were to take the limit as x approaches -5, we could see that that limit does exist because of this right here. So it's discontinuous at x equals -5, but because the limit exists, it's going to be removable. Now, at x equals 4, we would actually, if we were to graph this function, we would have a vertical asymptote. So this one would be non-removable discontinuity. Okay. And later on, we talk about vertical asymptotes. That's why at x equals -5, we'd actually just have a hole in the graph. Okay. Now, discontinuity happens with fractions, but it also happens with the piecewise defined functions. Just a quick mention of that. 13, we have, well, kind of a somewhat basic piecewise defined function. The function formulas aren't that difficult. They're both linear. But we see 3 different pieces of it. Now, one piece is when x is less than -1, one piece x is greater than -1, and then the third piece is just the single point when x equals 1, -1, sorry. So, in a function like this, where might a discontinuity occur? Well, it's definitely not going to happen at most of the x values. This is just a linear part. This is just a linear part. So the possible problem would be at -1. So we have to kind of look at what's happening from the left, from the right, and then does that match up with the function value? Okay. So it kind of goes back to our graph, the limit as x approaches something from the right, from the left, and does it match? Well, -1 from the left, theoretically we need to think of values like -1.1, -1.01, but in practical terms, we can plug -1 in here. What do we get? Okay, the technical terms, we can say the limit as x approaches -1 from the left will be, what, 3? And then this piece, limit as x approaches -1 from the right, what do we get there? Plug -1 in.
It's 3.
We also get 3. What's that tell us? These two parts? The limit exists as x approaches -1. And then this last part says f of -1 equals 3. Well, that happens to be the same value as the limit, so it is continuous at -1 as well as everywhere else. So this function is actually continuous for all real numbers. Now, of course, the difference, maybe the limit would be different from either side, or maybe the limit exists, but it's not the same as our function value. So there would be discontinuity at that point as well. So discontinuous, couple different types of problems. Okay. Then after we talked about that, we started looking at some applications of our limits, and we began with some average velocities and kind of led into the instantaneous velocity, which now we know is the derivative. Instantaneous velocity, given a position function, the velocity function is what? the derivative of the position. Okay. Well, we just finished the chapter that we went the other direction, but that basic idea, we started to see why, some of the theory behind it in this chapter. So position and then velocity is your derivative. Slope of the tangent line, well, that's also the derivative of your function. And at this point, we had not gotten to any of the shortcuts. We had to go the long route with those. But any of those application problems, I will allow you to use the shortcuts. So given a position function, if I ask for velocity, by all means use the shortcut derivative properties. However, looking at the last page of test 1, number 18 is use the definition of the derivative. And I can tell you there will be a problem like this on the final. If you use the shortcuts and get the derivative, no, you're still going to get it wrong. You got to go through the entire process. So do you remember the formula? It's the limit as delta x approaches 0 of f of the quantity x plus delta x minus f of x all over delta x. And it turns out once we get this set up, most of the work done on this type of problem is algebra. Evaluating, of course, this is kind of the tricky part. Make sure you evaluate that correctly. Lots of algebra operations, simplifying. Ultimately, it comes down to the numerator will be able to factor out a delta x, which will then cancel with this. And finally, we apply the limit. We actually do a tiny bit of calculus and come up with the formula for the definition of the derivative. So there would be one problem that I will specify, do this to be able to get the points for it. And then last two application problems, again, position, application, talking about velocity, and we kind of revisited that. But make sure you look over those and be able to answer questions given a position function, what's the velocity, and now we could even add what's the acceleration. But okay, that's test 1, and because that's been such a long time ago and we really haven't done a whole lot with limits since then, I took a lot of time on it. Going over the other tests, it won't take near that long. But we'll go ahead and start a little bit of test 2, which, well, most of test 2, in fact, problems 1 through 13, find the derivative of. And so test 2,
That's pretty tough.
using all those shortcuts and everything, there will be a few problems find the derivative of. And, well, that covers almost 3/4 of test 2. But you got your basic power rule, your product rule, quotient rule, chain rule, then all the trig derivatives. Make sure you know how to do those. Yeah, I know.
I'd be fine without all that.
Not too many people like trig, but it is a necessary evil. So that's pretty much well, the bulk of test 2. And then some of the applications or other slightly different types of problems. 14 on test 2 was given a function, evaluate the derivative at some number, f primed of 3, rather than find f primed of x, evaluate f primed of 3. So you got to find the derivative, then plug in 3 and find the derivative function value. 15 and 16 were using implicit differentiation. So make sure you can use implicit differentiation. Find dy by dx. And now 16 is find dx by dy, but on the final I'll limit it to just dy by dx. So kind of the normal order. Given something like this, okay, we don't have to explicitly solve for y and then take the derivative. We can use our derivative properties and be able to use the implicit differentiation to find dy by dx. Okay. Basically, the main difference, of course, the derivative of x squared with respect to x is 2x. Derivative of y squared with respect to x is what? Okay, 2y and then times dy by dx. And then derivative of 4, okay, is 0, thank goodness. Of course, I had to pick out one of the easiest equations to show you, but oh, you want that one on there? It may be a little more difficult than this, but same idea. And then we can solve for dy by dx. Or an application of this, given an equation in this implicit form, you might be asked to find the equation of the tangent line. Of course, that sounds like a problem we did later as well. Find equation of the tangent line at a certain point. So in a problem like that, well, your dy by dx, find that, plug in the point, the x and the y values, and dy by dx then gives you the slope. And then you'll have your point slope form to put it into the equation. And then the last 3 problems on test 2, again, that position. This time we do find acceleration as well as the velocity. But those types of problems, revisit those looking at it given position going that way, whereas this last unit we've been given acceleration and had to work the other direction. So that is really all of all of test 2. And tomorrow we'll look at test 3, 4, and 5. And then if there are any particular problems that you want to see, make sure and bring those and we can work through those. I think we'll have a little more time tomorrow to look at specific problems. So.
You didn't tell us which ones weren't going to be on the test.
Unfortunately, there's not really a lot of not on the test, at least in the first 2 tests. But